which we have done in the last 1 or 1.5 years. Actually, today maybe in some sense the last day of my PhD program, and also this is the last week of my stay in Davis. So let's start. Okay, here. So okay, so you can see this very lovely face. Let me call this a Higgs face, and this is I identified as 125 GeV state, which is which was discovered at LHC. And there are many other Higgs, heavy Higgs, charge Higgs, or more exotic Higgs, pseudoscalar, or something as a singlet, or dark matter Higgs, whatever. Let's just start. Okay, here this is the outline of my talk. I will first briefly introduce, I'll talk about the very updated precision measurements for 125 GeV Higgs at LC. And in the first part, I will talk about the SM-Higgs in the context of a two-Higgs-like model. And in the second part, I will talk about dark matter, Higgs being a dark matter candidate. All of these topics is written in my thesis. The title is Higgs boson physics beyond standard model. Unfortunately, it will be quite long or thick document. I'm trying to submit to you at the beginning of July. Okay, so far Higgs has been very standard model like Higgs has been discovered at LC 2 years ago, and by today, as of this month, CMS and Atlas has combined their data sets and presents the resulting result. So after all the combination, the final mass so far has been determined at 125.09 GeV with very, very small error bar. And then they measured another very crucial and important property, that will be the parity and momentum, to distinguish with a pseudoscalar or higher spin particle. And by now, all this hypothesis comparison with some other very exotic ones claims that this state is very compatible with the standard model prediction, that is 0 plus. And also, what about the signal? Let's look at. For the global signal strength in this very recent result is 1.24, a little bit enhancement, including this error bar even. And Atlas and CMS has given this channel by channel results. Let's call this as individual channel, individual production, and individual decay. So if you're interested, you can read my thesis, and all of this is put in one chapter. Anyway, the general conclusion is all the measurements shows this particle is very compatible with the standard model Higgs boson. But non-standard model or beyond standard model effect is still a possibility, although it is very strongly constrained. So the question is, are there only 125 GeV Higgs or maybe more? So in the first part, I want to talk about this BSM Higgs boson, and this is the structure of my thesis for one chapter. It's devoted to two-Higgs-doublet model, but I can't cover all the topics. In this talk, the content of this talk is based on 3 papers. One is we call it global fit to the latest LC data, which is published last year, and another paper especially studied lighter pseudoscalar boson in this model context, for which the mass is below 60 GeV, so that this 125 GeV and JV Higgs can decay into this pair of like Higgs pseudoscalar. And very recently, we are studying how to the difference between alignment and decoupling limits. All this I will discuss. Okay, so let's just take a very brief review about this two-Higgs-doublet model. Apparently, it is a very simple extension beyond the standard model. It just duplicates a complex through two-Higgs-doublets with a C capital charge, so that it will provide more physical Higgs states. In particular, the type 2 of this model can be realized in the super symmetrical version. And a very important aspect of the model is somehow it predicts the existence of a charged Higgs bosons if it is discovered in the future. This is the potential of this two-Higgs-doublet model in the of a Higgs sector. Here I eliminate lambda 6 and lambda 7 terms, which is eliminated by virtue of the hard C2 symmetry breaking. And for simplicity, we don't consider the explicit CP violation, so that all the lambdas, especially this lambda 5, and then 1, 2 square is assumed to be real. And also, we don't consider the spontaneous super CP breaking. So the phase, which is in this Higgs expansion, is also taken 0. But we allow this C2 symmetry softly broken. Otherwise, the tangent beta in this model is very limited, approximately less than 6, 7, and will not provide you a very rich or interesting phenomenology. So in this model, you see in this general basis, the free parameter will be like 5 lambdas and 1, 2 square. M1, 1 square and 1, 2, M2, 2 square can be derived by the minimalization condition of the Higgs value with respect to the V1 and the V2. And but for a particular purpose of phenomenology work, it will be convenient to choose this input set, which contains 4 physical Higgs masses and a tangent beta, which is a ratio of the 2 waves, and sine alpha, which appears in the CP Higgs mass matrix, together with M1, 2 square. Because then you can directly input the mass of your Higgs of your particular interest. After electroweak symmetry breaking, this model will provide 2 CP scalars and 1 pseudoscalar and a pair of charged Higgs. So far, people have studied in this model have studied a light CP or heavy CP even states being a 125 GeV state. What about the Yukawa sector? This is the general form of in the two-Higgs-doublet model for the Yukawa sector. In principle, both two Higgs doublets can couple with the females. But in order to eliminate, due to the very tiny contribution to the flavor changing currents from the BESM effect, we could just consider type 1 and type 2, which is just impose additional symmetry by eliminating, so that we can eliminate some combination in this Yukawa sector. In short, type 1 there's only 1 Higgs doublet coupled with female, stem-out female, while in the type 2, 1 Higgs doublet coupled with the up type, and the other Higgs doublet coupled with the down type and the left type. After electroweak symmetry breaking, we can rewrite the full expression of this full Yukawa in terms of this we call the C, or the reduced couplings, which is a function of the alpha and the beta. The pattern of this coupling is listed in this table. I won't go through it all of them, but just to point out here, you see this is a vector boson, Higgs coupling to the vector boson, and there is a very famous or very important relation among them. The square of the sum of the square of this vector, the coupling to the vector boson is 1. And in the two-Higgs-doublet model, a CP conserving two-Higgs-doublet model, this term is 0. So if one Higgs is very standard-like, then the others very, very small or negligible coupling with the vector boson. This will help to realize the one of the scenario at the capital H being 125 state. We will discuss later. Any question? Okay, since so far this GP hypothesis is very strongly or highly favor 0+, so we consider in our study we just consider the light CP even or heavy CP even being 125. And in early study we also consider the degenerate scenario, that is both H and small h and capital H very near 125. I won't go to this work in the talk. Okay. For our phenomenology study, we first consider or take all of these constraints into account, which contains pre-LC and LC8 or row 1, and also theta. So all the existing experimental constraints and theoretical constraints like stability, unitarity, predictivity, all of that we have considered. So the points which are shown in the following slides has been satisfied all these three groups of constraints. Okay, first we check what's the status of this two-Higgs-doublet model after LC row 1 data. Here, this is the results. We show the results in tangent beta versus cosine beta minus alpha, or sine beta minus alpha plane. Upper panel is a little h scenario, and lower panel is capital H scenario. Here you can see, as expected, this 125G Higgs is very standard-like with possible variation. Here, this is type 1 and this is type 2. For the capital H scenario, the negative value of the sine beta minus alpha is not so favored. And in type 2, in addition to this trivial branch, in which the Higgs coupling to the vector boson is very close to 1, and the Higgs coupling to the female up tap, down tap is also very close to 1, we have additional branch. Here we call the wrong sign Yukawa. And this branch, particular feature is this Higgs coupling. In this little h case, Higgs coupling to the down tap is -1. In the capital H case, the Higgs coupling to the up tap is -1. But both sine beta, the Higgs to the vector boson coupling is very close to 1. And also, what about this Higgs signal in these two scenarios? Here we can see this. We plot, we show the two most clean signal strengths. That is Brown-Brown fusion to gamma-gamma and Brown-Brown fusion to ZZ. In the type 1, first of all, in this model cannot predict a very substantial enhancement in the gamma-gamma because of the universal up-tap and the down-tap coupling structure. While in the type 2, it could be, because in the type 2, we can increase the Higgs coupling to the top quark to increase the Brown fusion. And meanwhile, we can suppress the BB decay to increase the gamma-gamma branching ratio. in the end, we can achieve a very large enhancement. It could be more than or larger than 2 or 3. So the next question is it possible to distinguish a type 1 and type 2? For this, we find this ratio, which could be a very, very crucial signal for this work. For example, here, in the type 1 case, if the gamma-gamma is enhanced, then the ZZ this ratio is less than 1. The situation is opposite in the type 2. So if in the future experiments can give a result, actually in the current LC, the very, very recent CMS Atlas combined result, they give this ratio, but the result is very close to 1. And also you can find some other similar ratio, the other ratios which can do the same work. And the other question is, what about if in the future in order this measure the signal will converge to the stem model level? For this, we do analysis assuming all the channel available channel converge to within the plus minus 15, plus minus 10, or plus minus 5% with respect to stem model prediction, which is illustrates. Here I give a different various rectangle to send out this feature. So in this scenario, even in the future, it's converged to plus minus 5%. It's still viable. But for capital H scenario and in type 2, if it is plus minus 5%, then this scenario will be ruled out.
Can you elaborate a bit on this? Why is that?
Sorry?
Why is that in this case you cannot make it? I mean, if you make the coupling all equal?
I mean this one?
Yeah.
Why it is, I see, okay. So in the capital H scenario, the other Higgs, so actually this is the coupling limit, but in the capital H scenario, the coupling cannot be approached. Because the capital H is 125, then little h must be lighter than a pseudoscalar. That's constrained by from the flavor physics and perturbativity. I will show you a mass correlation later. Okay. So next question is we have checked the currency status. The next question, natural way to go to this future prospects. So again, we follow this plus various higher precision level to study this the two-Higgs-doublet model. Here I showed on the right plot that is for little h 125, and the left plot is the capital H 125. And yellow is the most stringent or the most converged level to the standard model. That is plus minus 5%. So you see here, still we have already seen. So once this precision level is approaching close to the standard model, then the value of cosine beta minus alpha or sine beta minus alpha will quickly push to a small value, or the Higgs coupling to the vector boson will quickly push to 1. But tangent beta still remains unrestricted. So actually, to date, the value of the tangent beta in the two-Higgs-doublet model context is totally free. But in the second part, you will see we will find one way to fix the tangent beta in some particular scenario. And another interesting quantity, which is could be probe at the ultimate final LC phase triple Higgs coupling. We define this as CHH. That is the real coupling, real triple Higgs coupling in this model context with respect to the standard model, or normalized to standard model values. So here we can see again, if we go to this plus minus 5%, then there's this triple Higgs coupling is very close to, or converge to the state model prediction near 1, and here is a type 1, and this is a type 2. So in the type 2, this level is even out of the LC range, or in the future CEPC search region, certainly. And and also this is actually in some there's an indirect relation between the triple Higgs coupling with this quartic Higgs coupling. That is controlled this Higgs potential, which is relating to this baryogenesis problem, or the strong phase transition, which is we are working on. Then one should ask, what about the other Higgs boson search at LC round 2? So here I guess the upper panel is little h125 scenario, and the vertical line is charge Higgs is a pseudoscalar, and color is a heavy CP even. Lower panel then is a capital H scenario. So this is what to ask. If it is a capital H125, then there's a pseudoscalar. The maximum value for pseudoscalar is about 700 GeV. And charge Higgs is also at the same order. So the coupling cannot.
Is it obvious to get that limit for the mass of the pseudoscalar? Like why do you
because of this, you see, I plot there is a perturbativity.
Oh, perturbativity. Okay.
There's a relation between the charge Higgs and the pseudoscalar.
So this is what we talked about, and I think your scenarios, and some of them at any rate, violate our perturbativity constraint. Yes.
And in capital scenario, the type 1 and type 2 is almost the same, except for in the type 2, there's a constraint from the B physics which eliminated the charge Higgs below 300 GeV also. So there's no point surviving in the type 2 case below this blue dashed line. Okay, I think that is too horrible part. So in this scenario, could be heavy CP even Higgs be searched. So here I just want to mention one point that I highlight this magenta dash line, which is achievable level at LC round 2. So you can see here there are many points above this dash line. That means if it is presented, then LC round 2 have a large possibility to find this Higgs boson. We want to go through these details. In this scenario, the pseudoscalar search status, and the capital scenario, and pseudoscalar. One thing we can point out is like you can see that the tangent beta dependence in the type 1 and type 2 is opposite. This is because the coupling, pseudoscalar coupling to the up type and down type is opposite in the type 1 and type 2. One is the cotangent beta, the other is tangent beta. And this is a capital H scenario, the light CPE line research. So I want to here. So now let's look at I have shown you the many plots, which is the perspective for finding a heavy Higgs. Our current interest is study the light Higgs, which is below the 60 GeV. So I just take example in capital H125. In this scenario, both lighter little h and pseudoscalar could be light. So for example, if below this line or the little h below 62 GeV, then h could decay, capital H, or like it's called this target Higgs, could decay to little h pair, And if A is also below the 62 GeV, then H can additionally decay into the A pair. Now in this region, there's the only thing, H decay into the AA. But the problem is that in general, once this decay is open, then the branch ratio is crazily large, which is apparently excluded by the current LC search for invisible Higgs decay. So how to, the one ask, is this still possible or alive, this scenario? This needs a very fine-tuned, this needs a very fine-tuned in the parameter space. And additionally, I want to point out is in this little h or light Higgs scenario, is not allowed in the MSSM because of additional symmetry, but it could be possible in the NMSSM. Many people have been studied this scenario. So here, let's take a close look at the triple Higgs coupling that give you a very systematic way to find the points which are surviving in these various constraints, experimental and including experimental and theoretical. So here, this is the expression for the HAA coupling. So first, we can take a very simple estimation, like in this very extreme limit, sin beta minus alpha equals to 1. Then this coupling reduced to this form. And so in this scenario, little h 125, so we can find the strong correlation between the pseudoscalar and the beta and M12. The result is shown in this figure. That is the surrounding the region which is surrounded by this two dashed line. In the middle, the solid line indicates this coupling is absolutely zero. While this two dash, the dashed line expanding two sides, give an estimation for about 30% invisible decay branch ratio. But in this model, of course, we have to certainly consider this perturbativity region, which is here the solid shaded region is viable under the perturbativity constraint. So here you can see only that this overlap region that is surviving. So it requires a very fine tune in the M12 and the tangent beta space. But this gives you one type of the solution, which is showing this Jiang. And you see the overlap region occurs a small tangent beta. This is why Jiang is located below on the bottom part. Besides this, there's another the type, which we call, I mentioned, is a wrong sign Yukawa solution. So in this solution, we can see we rewrite this HAA coupling in terms of the Higgs mass and beta. And if at exact this wrong sign solution, that is sin beta plus alpha is also equals to 1, that gives a solution like tangent beta bigger than 6 and CV bigger than 0.95, but it will generate a too large coupling. But the interesting thing is, if it is not exactly just approximate, then you will find the second term would could achieve a cancellation with the first term, so that we can get a small HAA coupling. That's very surprising. But in here, I can plot this type of solution is shown in orange in this plot. And here you can see, here I also plot the M12 versus the cosine beta plus alpha to illustrate the feature of this approximate limit, at the approximate limit. Any question? Yeah, do it quick. Okay, so what about how to tell the experiments to distinguish or study this scenario, or how can we use the current experiment data to examine this scenario? Yeah, again, I showed a ground-ground function to ZZ versus ground-ground function to gamma-gamma without, the plane. And the Jiang is correspond to the trivial solution, while this orange correspond to the Yuan-San Yukawa solution. So most amazing feature, or the special feature, is here in this scenario, these two signal strengths cannot be simultaneously equals to 1. That means the standard model limit. And also there are strong correlation between the branching ratio for this 125 GeV Higgs to a pair of light pseudoscalar and gamma-gamma signal strengths, which is shown in the lower panel. That's all. And so now we studied 125, and next we studied the lighter pseudoscalar feature, the feature for pseudoscalar in this scenario. Here, to help the experiment search these points, we plot the Run fusion to go to produce a pseudoscalar, and the pseudoscalar decay into tau block here. So upper is a little h scenario, lower is a capital H scenario. And I can't go through this, but I can tell you CMS has already undertaken this analysis, actually, and we are very lucky to be getting involved in this work. And the name will be shown in the author. The title should be coming very soon. One more thing I want to mention in this capital H scenario is in this scenario, in principle, both little h and the pseudoscalar could be lighter than the half of 125. But if we include all the experiment constraints, like the physics and the lab, this both the light scenario is not allowed. That means either little h or pseudoscalar will be lighter than 60 half of 125. Actually, this makes our work, our life simple. Otherwise, we would have to consider two invisible decay modes. Okay, this is the result. I can't go through, but the approach or the method is almost the same. We studied capital H AA coupling and capital H little h coupling, and then give a result. Again, plus minus 5% is not achievable in this scenario. Okay, this is something else, the decoupling limit. I can go just tell you the solution or the results right here. If you just require a coupling like cosine beta minus alpha or sine beta minus alpha close to 1, it doesn't mean you are necessarily goes into this decoupling limit. It could be also in this alignment without the decoupling limit. As long as another quantity, here we call it Z6. Z6 is a coupling between, in front of this one Higgs, H1 dagger H1, H1 dagger H2. It is softly breaking the C2 symmetry in the Higgs spaces. Then we can define self-rate in the decoupling, or even we can define another thing, is double decoupling, which means in both alignments and decoupling limits. The Higgs coupling to the vector boson is very close to 1, and the other, except for the 125, all the other Higgs mass or Higgs is very heavy, for example, like heavier than 800 GeV. But this is not allowed in the capital H scenario, as I mentioned already. Skip this. So let's do a summary. So further, there are regions. Of course, the first one is 2HDM, type 1 and type 2 of the 2HDM can provide a very consistent picture of LC round 1 data. There is a region which lab constraint doesn't constrain at all in the little h scenario, and a partial constraint in the capital scenario in our light Higgs study. In the presence of a light Higgs, the signal strength of this 125 GeV Higgs cannot be, or dynamo-like, and LC has begun performing analysis for the light pseudoscalar search. And in addition, if there is if such light Higgs is detected, then the models such as MSS will be eliminated, or a strong preference in favor of a general two-Higgs-doublet model will arise. So let's just waiting for very excited LC round 2. Any question about this part?
So did I see correctly that your search is for an 8 GeV Higgs boson?
Yes.
So are you trying to start a rumor?
No, not
No,
so. Not
eight.
8. Not
Why
less
did that
than
number
8.
8 was
come
the
from?
original LHC energy.
You mean 8
8
GeV?
GeV, I thought.
Oh, maybe
No.
I didn't see that.
No, our point starts
back quite a way.
10 GeV. Below 10 GeV, the early result constraint
There.
for the oops
Oh,
also.
8 TeV, I'm sorry. I just misread it. It says 8 TeV. I know where that number comes from.
Okay.
Sorry. Okay.
Okay, let's go to the next part. That is link.
We are very interested in very light
Sure.
Higgs
8,
bosons. And in this two-Higgs-doublet model, we have these huge cross-sections in general. So
Right.
The next part is let's call it linking Higgs to dark matter. And there are many scenarios for this interacting massive dark matter. Here I just highlight 3 possibilities. While the asymmetry, if we impose asymmetry in the supersymmetry model in general, we can achieve MSS, LSP dark matter, or even in the NMSS. Actually, this is what we have studied in my first 5 papers, and I won't go through this today. And another possibility is introduce extra dimension and construct a symmetric geometry setup. Then we have this Kiki exactor parity or symmetry. In this setup, we can generate Higgs-doublet being a dark matter candidate. This has been studied in our paper, collaborating with our Polish friends. Also, I won't go through this. So today I will talk about with this protection by the C2 symmetry. We can introduce a singlet Higgs singlet to the standard model or to Higgs-doublet model, and generate a possible dark matter candidate. So all this part of work is based on our another 3 papers. One is already published, the other is in the middle of working, and the last one is just mainly focused on the indirect detection with some guys. Okay, to date, the evidence of existing of the dark matter is quite strong, like from the bullet cluster and CM. What's this? And this galaxy rotation curve, and also the Planck 2015 results, and also the measurement of record abundance has been very, very precise with this tiny error bar, 0.001. Okay, the main motivation for our work is something message from the main dark matter direct detection. So I hope I show you the very recent updated results of the direct detection. This is a LUX, and this is super CDMS, and this is CDMS2. So you can see for the LUX imposes the strongest exclusion limits in almost overall range, except for a very small range, which is controlled by or determined by the super CDMS. And another thing is the signal region claimed by the CDMS2 is entirely excluded by the LUX if we assume the dark matter has the same coupling to the up and the down type. That means the isospin symmetry is preserved by dark matter. And also in this translation, from the real experiment data to this plot, experiment guide, I think, made a couple of assumptions, maybe two rules. Like first, we do the standard model, halo one. Like this means dark matter distribution is spherical, and also the short range interaction. And what I have already mentioned is the equal coupling to the proton and the neutron. And last is assume this scattering is elastic. So question is, are they all true? Or maybe something too root, and then we missed some important message. So here, I just want to point out one possible relaxation is if this FNLP, FN denote for the dark matter coupling to the neutron, and FP is dark matter coupling to the proton. If this is not one, then we need a rescaling factor to interpret the current experimental results, which was originally studied by Jonathan Fong's group in 2011. So here I just show you the results. If for example, if this FLP is minus 0.7, then this is okay. I have to explain. Horizontal line is the dark matter or the dark matter mass, and the vertical line is the dark matter nucleon cross section as a function of the FLP. So solid line is for FLP equals 1, and dashed line is for FLP equals minus 0.7. So here you see if the FLP is minus 0.7, then the CDMS2, which is shown in purple, it's called purple or light dark blue, is partially excluded by the lux, which is shown in the green, dark green curve. So maybe this is a good direction to study dark matter and try to relax this constraint. I don't know, but just let's try. Okay, in order to study this isospin violating factor, we carefully calculate this FLP in a general Higgs mediator model context, in which the dark matter nucleon or a certain flavor of quark interacting by exchanging a T-channel Higgs. There could be one Higgs, there could be multiple Higgs, it doesn't matter. Here I just give you, this is the full expression. And the capital F is some combination of the form factor. While if we include this ground fusion, or no, sorry, not ground, include this QCD next leading order effect, which is highlighted in red, will give you an additional factor in the form of this capital F. So here I show you that if we plug in all the known parameters, then plot the FLP as a function of the effective coupling of this Higgs dark matter to the up type and down type. This is the result. And the black curve is just without this QCD correction, and the red curve is with includes the QCD correction. So here you can see if FLP is minus 0.7, then the ratio of this lambda U over lambda D will be around minus 0.9. But the result is very sensitive to the QCD correction. So that thing. And also if we additionally include the chiral correction in this interaction, then the result will have another further shift. So that's not so good. I think that we have to consider higher order correction to stabilize the result. But okay. So the minimal or the the minimal extension is just adding a singlet to the standard model, which is called standard model plus singlet model, and which is studied by many guys, in particular this first group 2 years or 3 years ago. And this model has a big problem is if this singlet being dark matter candidate is very light, lighter than half of 125, then the branch ratio for 125 GeV to this pair of singlets could be too large if we want to satisfy this relative abundance constraint. And also, and also the dark matter nucleon cross section will be too high in the low mass region, which is absolutely above the Lux limit. So it seems that we have to extend, go beyond. Let's go beyond. That is, we add a singlet in the two-Higgs-doublet model. Here you see there's many. I give a cartoon to show what we did or what we consider to do. Is in this model there are two Higgs, and both two Higgs will have an interaction with this dark matter. But if this is 125, we can switch off this coupling so that Higgs will not decay to singlets. And then the invisible decay branch ratio is just 0. And it will still have another Higgs, could be, play with dark matter and then respond, generates the correct relative balance. So this is the advantage of this model, which is good.
Can I just ask, is this for heavier dark matter, is the singlet model okay?
Yeah, okay. Because there's no constraint, the Higgs will not decay to the...
That's the only difference.
Yeah, but we are interested in the low mass region. And also, let's just consider the type 2 model, because in this case I show you, if in the type 1, all the Higgs has the same coupling to the up type and down type. So you will give this lambda, the common factor, find out, and after P very close to 1, maybe not exactly 1, because the form factor is not the same, exactly the same. So we just consider type 2, which might give an isospin violation effect. I'm not sure how much I left. So we call this a 2HDMS model. In this model, we add a real gauge singlet in this two-Higgs-doublet model. We have this generates produce the potential. This line, which will show in the last line, and we impose the C2 symmetry, on which S is odd, while both two Higgs-doublet is even. And also there's another C2 symmetry which is embedded in the original two-Higgs-doublet model. So this model has a symmetry C2 cross C2 prime. And with this C2 symmetry protection, this has to be singlet to be stable, and it could be dark matter candidate if this S doesn't develop or acquire a valve. Okay, this is if we expand the potential in the singlet sector in terms of Higgs mass, not Higgs mass, in terms of this no. After the electrosymmetry breaking, expanded this. Just give a list of those couplings. Just give a remark. In this coupling, there's no direct AS squared term, but it doesn't mean S or pseudoscalar. It doesn't mean pseudoscalar doesn't play with play a role in the dark matter physics, because there's still AAS. Okay, there's still AAS direct or contact interaction. But in this model, additional independent inputs could be MS, the dark matter coupling with the real physical light Higgs and physical heavy Higgs and dark matter self-interaction. But for simplicity, we switch off one coupling, as I mentioned already, and dark matter self-interaction doesn't, there's not so significant in our study, so we just left with 2 parameters. Okay, here, before the phenomenology study, we seriously consider or study the theoretical constraints derived from this stability, unitarity, and perturbativity. But due to time, I can't go through this. And in the end, after including all these results, we will find that this is red points. And the lambda little h and the lambda capital H both have to be very small. Just one slide. Good. So here, let's just study dark matter physics in this model. It's very complicated. Just here, this is all the Feynman diagrams contribute to this SS annihilation. It could be the SS annihilate by interchanging S-channel Higgs. This is also present in the minimal standard model plus singlet version. And additionally, we have SS Higgs contact interaction and SS SS via S-channel Higgs, but final state is also Higgs, and also a T-channel exchange, S exchange. So our strategy is switch off one Higgs coupling and let the other Higgs play the game in the dark matter. So I don't go this. Just show the results. So in the type 1, it's almost the same as the standard model plus the minimal singlet extension model because it's almost the same. Just add an extra Higgs. So in the low mass region, the points you can see is above the lux limit, while in the heavy dark matter, it's okay, it's below because there's no constraint from the invisible decay. But what we are interested in is the type 2. Here, I show you is the expression of this tangent beta in terms of FRP value. And W is we call the weight parameter characterizing this Higgs exchange. But if one Higgs is closed, for example, if the little h is closed, then this W is 0. If the capital H is closed, W is goes to infinity. Then I translate this expression into this three-dimensional graph, which is a tangent beta versus sine alpha, and the dashed line. This direction dashed line is drawn at various FOFP region from minus 0.8 to the plus 0.8, and this direction dashed line then indicates the value of the sine beta minus alpha or cosine, the value of cosine beta minus alpha. Actually, this indicates the value of the Higgs boson to the Higgs coupling to the vector boson. So the most most inner dashed line is the value, I think is 0.99. So that means even when this Higgs 185 GeV Higgs is very standard like, this dark matter could still have generate a value for this FRP at minus 0.7. So there's no any conflict between the Higgs and the dark matter result. Actually, I think this is our very first result. Very fine-tuned. Why? Actually, here I plot the sine alpha from minus 0.85 to minus 0.8, and tangent beta from plus 0.7 to 1.3. So in the overall, in general, in the two-Higgs model, tangent beta could be from 0.7 to 60. So that means this point is just located at the overall picture of two-Higgs at a very small, let's call it the left bottom corner. So it's really very fine-tuned. So if you just submit a random scan in the overall 2HDM space, it's very, very little chance you can get a point. Even in this small region, as long as you submit points along this narrow strip, If we want to minus 0.7, it would be here, very narrow strip. Okay, with this cancellation, because in this the coupling F, and I have already shown a couple of early slides, the ratio lambda u over lambda d is negative. So with this destructive contribution, then the dark matter nucleon cross-section in the low mass region could be quite low, so that not escaped by or eliminated by the Lux limit. You see, here I plot the results as a function of f over p. I'm pretty sure this is a minus 0.8 to the minus 0.7, and on the top there is a plus 0.8. And I also show the results, just to plot the points which below the Lux into silicon-based detector and germanium-based detector. Actually, our original purpose is to try to find the points which could simultaneously satisfy the Lux and the CDMS2. But in the end, we failed. But occasionally, we find this mechanism to suppress the dark matter nucleon cross-section in the low mass region. It is a capital H scenario. So, as you remark, Higgs and dark matter sector may be ultimately intimately connected. If so, detecting the sign of one-off sector could shine light on the hidden sector. It is certainly of great interest to explore some of the implications of the recent development in counting Higgs and detecting dark matter in the context of a very simple framework, as simple as possible. Okay, the last thing I think we left with the biogenesis. We're trying to work out. Oh, in the end, I gave a comment that dark matter study is becoming more and more complicated. However, maybe we are approaching the realities step by step. Okay, thank you. And I want to do one more thing. I hope you can still around. Since this is probably last day of my PhD program. So what's up? Okay, thanks, Jack. Thanks for what you have done for me, all the things in the last 5 years, and make all possible efforts to achieve my success. Just let me just briefly review what we call the review. Actually, in 2010, I met you first time in Singapore, and we had a very pleasant conversation. And after that, I decided I come to here. And of course, you gave me an offer. And then, okay, then have my growth at Davis. And in the first year, I'm very lucky to have 6 papers with you and our collaborators again. She's really a very efficient worker. And then second, in the 2013, I call this as my conference year. Actually, I attended many conferences, and we took a picture in Warsaw. Hope you still remember. And this is a Grenoble, France. And then this year, because of so many publications and other activities, I won 2 prestigious awards. But unfortunately, missed this award ceremony because of your health condition. But very good. Even the second day you have an operation, you still attend another ceremony for me. I call it award year. So much. And they reach for me about 15 publications and about 500 citations and more than 40 talks, blah, 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 and also 5 awards. So let me just say, meeting with you is a huge luck throughout my life, and I'll be dreaming to the future. And of course, in the last best wish, we have a good health. That's most important. Okay, then. On Thursday of my commencement, and welcome to attend. And I give a question mark here, so nobody knows what happens of this year. So thank you, and it's an amazing time for me here.
questions for you? I have a short one. Going back to the first part of your talk, in the CMS search for light age came to be 2 tau tau, right?
Yeah.
What is the search triggering on? Is it triggering on the forward jets or on the taus?
Well,
Can we say something here? This is because
I mean, just qualitatively, no one know any technical details.
there's no something I show here because we don't.
Well, I can just summarize, the basic, it's tubular fusion, right?
Right.
So.
No, wait, it's BB fusion or gluon fusion?
Tubular fusion.
Oh, okay. No, I'm sorry. Then it has to be on the
It's
taus.
not the forward factor jet, so.
No, I thought you were looking at the BB bar.
Maybe.
Oh, for the BB bar, yes. So
They
you
consider-
do the B trigger.
Right.
So it's a question of which cross section is biggest.
So you're looking at both?
Yeah,
Okay.
yeah,
No.
the CMS experiment is looking at both. They're
But group
about to produce a BB Higgs result,
Okay.
which we'll see, but they're looking at both, yeah.
Okay, if there are no further questions, let's thank you again.